Hello everyone, we are still talking about sorting algorithms. The next sorting algorithm that I'm going to discuss with you is merge sort. The idea of the merge sort is a recursive idea. Actually, the idea is very simple and neat. It says that if you have an array of size 0, or if the array is just one item, it is already sorted, right? You don't do anything to sort just one item or nothing. And if you have any array greater than size 1, what you need to do is you can just divide the array to two parts, sort each one recursively, and then merge two sorted arrays into a larger array, and you are done. Okay, so this is exactly where the recursive part is coming. That if whenever you have an array of size greater than 1, you do divide it to two parts, recursively sort the array. So as you can see, the idea is that you just make the problem smaller and smaller until you get the problem of size 0 or 1, which is the base case. If it is of size 0 or 1, you don't need to do anything. It is already sorted. And for all when you actually come back from the recursion, you have two sub-arrays which are both of them already sorted. You need to merge them. This idea is very important because this is one of the main examples of the divide and conquer approach. In COMP251, the design and analysis of algorithm, you will learn about many problems that can be solved using this paradigm. Just try to divide the problem to some smaller size problems, solve them. So the idea tells you that divide the problem to smaller sub-problems, solve them, conquer each smaller sub-problem, then you can actually just merge the solutions and get the solution for the larger problem. So I'm not going to emphasize on this idea, this important problem-solving technique, which is basically a recursive idea, but let's actually just get back to merge sort. So assume that you get an array of size 8, something like this. Because the size is greater than 1, of course you need to divide it to two parts. You find the middle index, which is going to be the index for actually 5. You divide it to two parts. One part is this part, the other part is this part. Recursively call merge sort over each one, sort them, and then just assume that, okay, I'm not going to actually do all the steps. Just assume that you get this one sorted and this one also sorted. So this is the sorted form of both two parts. Now I'm going to emphasize on that merge part. How can I merge two already sorted arrays? If I have two sorted arrays like this one and this one, basically two sub-arrays, I wanted to merge these two to get a larger array, which is going to contain all the elements in the original array, but now they are sorted. The question is merging two already sorted sub-arrays easier than sorting the whole array originally or not? And if yes, how can we merge two sub-arrays which are already sorted? So this is the question that I'm going to answer first. Okay, if you think about the idea, you have two sub-arrays, this one and this one. Both of them are sorted. I'm going to merge them and get an array of a full array that contains all the elements in these two sub-arrays. If you think about all the items in the first array, the smallest one is going to be the one at index 0, right? This basically actually index. The smallest one in the whole array here also have been actually stored at the first index, right? So the smallest item among the set of all items is going to be either this index or this item actually at this index. So I don't really need to check all the items. This array is already sorted, this array is already sorted. I can just by comparing the starting from the first index in the first array and the first index in the second array, just compare these two and get the smaller one. This is going to be the smallest among all of the items, and you just need to put it here, which is going to be the item, the number 2, right? So the idea is that after you copy 2 as the first item, you can see that I have updated the counters. I have updated the index here, and I also updated the index here because I have already copied 2, right? So this actually index will be increased and go to refer to the next one. Then I do exactly the same. Compare the item. You can see that I haven't actually updated this index. This index is still actually referring to 3. Now you compare 3 and 7. The smaller one will be copied in the in the bigger array that you are creating. So 3 will be copied. Then you are copying from the other array, so the index of the other array will be increased. Now you compare the elements again at this index and at this index. The smaller one will be copied here, which is going to be 5. And then this index will be actually increased. Then you actually compare this one and this one. The smallest item is going to be 7. 7 will be actually copied here, and this index will be increased. So that's it. You actually just continue updating only the index over the array that you are copying from, just based on the comparison. So you can see that here in this case, I have copied 7, then copied 12, then copied 16, all from the second array. And then I started copying 18, 21, and 24 from the other array. Okay, and continue. You continue until when the size of these two arrays, this one and this one, is limited. At some point, either this index or this index will reach to the end of the array, right? So you would continue until one of the indexes reaches to the end of the corresponding array. After that, the rest of the items will be just directly copied at the end of this bigger array that we are creating. And we are done. So what is the time complexity? You can see that we are filling this larger array, right? So we are basically, if the size of the larger array is this array, assume that this is n1 and the size of this array is n2. So the size of the larger array is going to be n1 plus n2, right? And for filling each index, what I do is just comparing two items, get the smaller one, copying it here. So this is going to be constant amount of work. So for each item, you are just doing constant amount of work. The total time complexity is going to be theta of n plus 1 plus n1 plus n2. Okay? If you think about the original problem that we have, usually the size of because we actually divide the size of array to 2 parts, n1 and n2 are going to be almost equal to each other, right? You always actually divide the original array to 2 parts. Either they are going to be equal size if the size of the array is even. If the size of the array is odd, one of them is just one index, larger than the other one. But we can actually assume that n1 and n2 are equal. So in total, the time complexity will be just linear. Here it's just discussing that why the time complexity of merge is linear. Now let's actually get back to the merge sort algorithm. The idea of the merge is that you if the size of the array is greater than if the size of the array is greater than 1, you need to divide it to 2 parts, right? And recursively call the merge sort over each part and then merge them. So let me actually show you the whole merge sort algorithm over an example. Just assume that I have an array of size, for example, 8. I just choose 8 because this is a power of 2 and makes it more clear. But even if this is not a power of 2, that's totally fine. I mean, the procedure is going to be exactly like what happened here. So the size of the array is greater than 1, right? So you divide the array to 2 parts. So this is going to be the first part. You then recursively, when I'm actually saying that you divide the array, it basically means that you find the middle index and you would say that, okay, this is the first part and this is the second part. This is the first half, this is the second half. Then you recursively call the merge sort over the first half. So it is just like, this tree that I'm showing to you here is just the function calls. It's just like this is the function call for the original array when you are actually merging over the original size of the array. Then if you call the merge sort over this part, this is going to be the function call over the first part. Then again, in the definition of this recursive function, you would check the size of the array. If the size of the array is greater than 1, you have to divide it to 2 parts. So you find the middle index and you would say that this is going to be the first part, this is going to be the second part. I recursively call the function over this part. So this is going to be the function call. Okay? Then you check the size of the array is still greater than 1. You have to divide it to 2 parts, right? You find the middle index and you say that this is the first part, this is the second one. You call the recursively over the first part, which is going to be this recursive call. Okay, now the size of the array is 1. Your recursive function is not doing anything, just return this array. And you would say that, okay, an array of size 1 is already sorted, just return it back. So that's why you can see that I have written that we go back in the recursive, you call it over the first part, which was 81. It is sorted and the function call is coming back. Then you call it over the second part. This is going to be already actually sorted. So this is a function call. It checks. This is the base case of your recursion. The size is 1. So you just go back and say that this is already sorted. So now you have 2 sub-arrays, this one and this one. Both of them are sorted. You merge them. And you get a larger array. The full array here is already sorted. It is sorted and the function call will return this array and say that this is sorted. Okay, so this part, in this function call, you will see that this part is already sorted. You call the merge sort over this part to sort this one. So this is the function call. The size of the array is greater than 1. You divide it to 2 parts, right? And you call the function over this one and call the function over this one as well. So you first call it over the first part. This is the base case, right? We recursively call the merge sort over the array of size 1. The size is 1. This is already sorted. So the function call will return and say that this is already sorted. Then you call it over the second half. So recursively call the merge sort over this array, which is of size 1. This is again a base case. You would stop and the function call will return, say that this is already sorted. So you get this part sorted. This part is also sorted. Now merge them. You merge these 2 arrays and okay, you get a larger array of size 2, which is completely sorted. This array will be returned to the previous function call. Okay, now in this function call, this half is already sorted. This half is sorted. This half is also sorted. We have to merge them. The merge method that we have will merge these two and get a larger array. This array will be returned to the very first function call. Okay, now in our first function call, this part is sorted. We have to call the merge sort over this part. Okay, you call the merge sort over this part. And again, I'm not actually going to completely show you all the steps here. Again, you would divide the array to two parts. So this part you call actually the function call over this part. Then you call it over this one. 17 is actually already sorted. 31 is already sorted. Then you get these two. You would merge them. And then you would get the full array which is sorted. Okay. You get the first half sorted. The second half sorted. And the whole array here will be actually sorted. Then this part will be returned to the original function call. This is the very last step actually. In the original function call, this part is already sorted. This you call it and sort this part. You called and sort this part. Now you merge them. So this is going to be the full array. The whole array is already sorted and you return it. So now I'm going to show you the code. The recursive part of the code, the merge sort. You can see that the code is very simple, just a few lines of code. But there are some details that I would like to discuss here. One thing is that the merge sort algorithm that I write here is of type void. Why? The reason basically is that I don't like to, whenever you have specifically the recursive functions, try to don't return array, because there will be a lot of function calls, right? And if you keep creating new arrays, or if you create new strings, doesn't matter, if the item that you are working on, the object that you are working on is an array or a string, if you keep creating new strings and just return them, you would take a lot of space from the stack. So there is a chance that you go with the either a stack overflow, or even if you don't actually get a stack overflow, it is very, you make the code very inefficient, because passing arguments, creating and passing arrays again and again and again is going to take a lot of time, because the function is recursive and you might have a lot of function calls. Okay, so avoid passing arrays and strings when you are working on recursive functions. So how can I make sure that I can implement merge sort by not passing the array? Especially because I'm working on array and I'm actually telling you that, okay, create a smaller array, call the merge sort over the smaller one. The trick here is that I would pass just the original array. Always I would pass the original array. But in addition to, when you are actually passing the array, you are not really passing the full items. You are only passing the reference. So that's why passing it as an argument is not going to take much space. But when you are actually returning, this is going to be copied. So avoid, returning arrays or a string. Okay, the trick is, instead of creating smaller arrays, I am going to pass two arguments, first and last, which basically tells me that which part of the array you are working. Okay, so if you are working on over actually the full array, at the very first, your function call will be, okay, pass the array, and over an example like this, it will be actually index 0, which is going to be the first index, and index, for example, 7, which is going to be the last index, right? This is going to be index 0, and this is going to be index 3, 4, 5, 6, 7. Okay, So this trick, you have seen that the same trick when we worked on checking the palindrome and some other actually examples that we discussed when we talk about the recursive algorithms. And so, for example, when you create a smaller array of, for example, the first half, you would call the same function call by passing, for example, pass the array index 0 and index 3. So you would know that you are working on this part of the array. For example, over this function call, if you are passing this part of the array, pass the array index 4 and index 7. Okay, so that first and last are basically telling me that which part of the array I am working on. Okay, so the base case, remember, when you are writing a recursive function, you have a base case and you have a recursive part. Remember, I told you that the base case is when the size is either 0 or 1. Okay, so if I am actually passing, I can actually check the size of array A because it is always the original size, but first and last tells me that what is the size of the array. So basically, if the first is going to be, for example, this is going to be the first, this is going to be the last. Okay, so if first and last are equal, something like this, first and last, both of them will be actually 0, for example, in this case. Both of them will be 1. Both of them will be 2. Okay, if first and last are equal, it tells me the size is 1. So if first is equal to last, it basically tells me that the size is 1. What if the first is greater than last? Basically, first greater than last tells me that there is nothing in the array. The size of the array is 0. So these two cases are going to be the base case that I need to check. Instead of checking these two, I can say that, okay, if the first is smaller than last, it means that there is still something in the array to check. So for example, when first is equal to 0, last is 1, index 1, it tells you that, okay, there is still, for example, just 12 and 34, for example, something like this. You are working on array of size 2. Okay, still last is greater than first. So I am implementing the base case in this way, that if first is if first is greater than last, or if first is equal to last, these are the base cases. So if first is less than last, this is going to be the recursive part. Basically, I have tricked the code and make it, look much smarter by just not writing the base case. Basically, if this if a statement is false, it means that it will be the base case, and you see that there is nothing in the code to do. So the function will just return. The function doesn't do anything in the case of the base case. So if first is smaller than last, it means that there is still something to work on. The size of the array is greater than 1. I need to divide the array to 2 parts. So something like this. If I need to divide, this is not exactly the position, but anyway, you need to divide let me show you another example. For example, here, you wanted to, let me just remove this. Okay, just assume that you call the function over this part of the array from first is here, last is here, right? You want to divide the array to 2 parts. How you are going to divide the array to 2 parts? You wanted to find the middle index. So what is the middle index? The middle index will be first plus last divided by 2. What is first? First is basically actually index 3 in the original array, right? And last is going to be index, for example, 7 here. Sorry, index 4 for the first. 4, this is going to be index 5, this is going to be index 6. So if you want to find the middle index, you have to add first, whatever is first, first plus last. Be careful, I am adding first and last. I'm not working on the original size of the array, because the original size of the array was 8. But the size of the array that I'm working on here is going to be from first to last. So first plus last divided by 2, it is going to give me the middle index. Let's just call it mid. In this case, first is going to be 4, last is going to be 7, this is going to be 11 divided by 2. This is integer division, so it's going to be 5. So this is index 5. So it tells you that from first till the index mid, this is going to be the first part. And from index mid plus 1 to the last is going to be the next part, the second part. If I show you, you can see that I am calling the merge sort recursively, passing the original array, index first, and this index centered, so center or mid doesn't really actually matter. I'm using a different variable name here. So here center is exactly that mid. Okay, so first plus last divided by 2 will give me center, and you call the merge sort over first and center, and then call the merge sort over the second part. So this is going to be first part, first half, and this is going to be second half. Okay, from center plus 1 to last. Okay, after we call them recursive, so you see that here is just the recursive calls. After you are done with the recursive calls, you will need to call the merge method. Okay, so I'm going to discuss about the implementation of the merge. So as you see, again, when I am merging two subarrays, I don't want to, pass and, return. You created more and more copy of the array. Merge here, the method merge, there are different ways to implement method merge, right? But the way that I'm implementing it here, I am trying to just merge these two halves and put them inside the original array. So I am passing the original array, I am passing 3 indexes as well. First, center plus 1, and last. Which basically is going to be, for example, here you are passing 4, passing the index 5, and passing the index 7, which basically tells the method merge that from index first to index mid, this is going to be the first part of the array. From index mid plus 1 until last is going to be the second part of the array. Okay, this is going to be the implementation of merge. Sorry that I'm using a different set of variable names here. At first, when I was writing the slides, I thought that if I use different variable names, it makes it more clear. But maybe if I use the same names, that would be easier. But anyway, this low here is going to be that first. Mid here is going to be the variable center. And high is going to be the variable last, if you think about it. So this is going to be the first. This is going to be the center plus 1. I mean, that variable mid is going to be center plus 1. And the high, the variable high is going to be the last variable that I'm passing. So this is important to know that what is the second argument. I am passing center plus 1. This means that from array index first over the original array, if you think about it, wherever is first, this is going to be mid, and for example, let's just assume that this is going to be last or high. Okay, so this way, this is going to be low, high. Let's just call this one mid and say that this is going to be center plus 1. So basically that center plus 1 was a part of the the second array, right? So this is going to be the first array, this is going to be the second array. I actually write it as mid in this way because excuse my handwriting. Okay, it tells me that the algorithm, we already actually discussed the algorithm. This is just the details of the implementation. I am trying to make sure that after I am done with merge, I'm not returning the merged array. What I'm going to do is that just copying, I need to create another array, okay? This array that I'm creating, this temporary array that I'm creating is here. I need to create some additional array because I cannot do the merge in place. If I am copying from this side of the array and this side of the array, I cannot actually rewrite the result exactly at the same time here. I need to create some additional array that here I'm going to call it the temporary array. But when I'm actually iterating over these two arrays, I will copy the elements inside this temporary array, and then at the end in this loop, I will copy back everything from temporary array inside the original array. So I'm going to discuss about that later. Just let's actually stick to this, what I am doing here. The algorithm was that you created 3 indexes, right? One index that starts here at the beginning of the first part, one index that starts at the beginning of the second part, right? The first index is going to be called I1. You can see that I have initialized it as low. The second index is called I2, and I have initialized it as mid. Be careful here, mid is a part of the second array, not the first. The part of the second half. Okay, so Y1 is referring to this index, Y2 is referring to this index. I initialized Y1 as low, Y2 as mid. So this loop is basically just checking that until Y1 and Y2 hasn't reached to the end of the first half and the second half. So I'm comparing Y1 to mid because this is the upper bound for I1 and this is the upper bound for I2. High is until I2 is smaller than high. And I'm actually just writing it as smaller than or greater because the index high is also a part of the second half, right? But the index mid is not a part of the first half. That's why these are just the details of the implementation. I'm sure that if you try to trace it over an example, everything will actually sit in place. So this loop just iterates over I mean I1 and I2, just compare it. Always get the smaller one and copy it inside temp. So there is another index, we call it J. J is initialized at 0. J is the index that iterates over the TMP. So either you get the value from array index I1 or array index I2, whatever is smaller. If array index I1 is smaller, you get it from, you copy that to J. If the other one is smaller, you copied the other index inside the index J. Okay, these two loops here, only one of them will be executed in practice, right? Because when you are stopping this loop, either this is true or this one. Whatever is going to be true, you can see that if, for example, this case is true, this loop won't iterate. If this one is true, this loop won't iterate. So I'm just writing both sides of it. Either you copy the remaining element from the first half, or you copy the remaining element from the second half. You copied all of those in the temporary variable. Then now we are actually coming to the last part. The last part, until actually this point, we are done with copying all the elements inside TMP. TMP is that additional array that I have created, and merge the first two halves, merge this part and this part. Now I want to make sure that when I am leaving the method merge, I don't want to pass an array, because I don't want to actually, copy and paste. When you are passing an array, as you are returning an array in the function calls, it takes time. This is not efficient. So that's why it is actually much easier that the size of all the variables, all the values which are here in TMP are exactly the values here and here, right? And we wanted this part to be copied exactly in this part of the array. So what I am doing here is that I'm just exactly copying all the indexes from the temporary array inside the original array. But where the indexes in the original array should start from the index low, right? So be careful. J is, for example, if J is 0, the corresponding index is going to be low. You just copy from index temp index 0 inside low plus J. So in this way, you would actually just make sure that you are copying exactly from index low until index high. Okay, so if I call merge, just this example is a very imaginary example. This is not a real example. Just assume that over a very large array, you see that these indexes are not 1 and this is started from 9 or something. This is a very imaginary example. Just assume that you call merge somewhere at index 14, 20, and 25. It tells me that low is 14, high is 25, and mid is 20. Which means that this is the first part from low until mid minus 1, from mid to high. This is going to be low, mid, high. So you can see that this is sorted, this is sorted. When you call merge, it should merge them and make sure that it merges it inside the array. So after you are done with merging, this is going to be the result in the original array. I'm not returning any array. I'm just copying everything inside the original array again. So I'm done with the algorithm for the merge sort. This was the recursive algorithm with the recursive calls and the merge. And this is the implementation of the merge. Sorry that it actually looks like a mess, but in the original slides, everything is clean. Study that. Now I'm going to actually talk about time complexity. So what is the time complexity of this method? Let me actually just clean a little bit here. I'm going to keep this base case to just actually makes it more clear. Okay, so the time complexity of the merge sort is a recursive algorithm, right? The only thing that I know is that the cost of the method merge is theta of n. When you are actually merging an array of size, two arrays of size n divided by 2, the time complexity is going to be linear, right? But I can't actually, analyze the time complexity easily because this algorithm is a recursive algorithm. The way that I'm going to actually discuss this is something very nice. You can actually simply assume that, okay, usually whatever is our code, you would define some time function t of n for your algorithm, right? Where n is the size of your problem. So what is n here? In our case, n is going to be the size of the array, which is going to be last minus first basically for us, because the last and first tells me that which part of the array I am working on, so what is going to be the size of the array. So the whole time complexity is going to be t of n. I wanted to know that what is going to be the t of n. You know, if your code is not recursive, you would probably find something like, okay, 6n power 2 plus 10n plus 100, something like that, right? This is a function in terms of n. But I don't have a regular function here. The function that I have is a recursive function. What is going to be actually the time complexity here? The time complexity here depends on the size. It tells me that if the size of n is greater than 1, you have one possibility. If the size of n is less than or equal to 1, which is going to be this base case, the time complexity is going to be constant, right? Theta of 1, because basically you don't do anything, right? If a statement is false, you don't do anything. So we would say that this is constant. But if the size is greater than 0, the cost is here. What you are doing here is that you are merging, which the time complexity of that is t of n, and you have two other function calls. You are calling the same method. You see that you are calling merge sort twice. But the size of the problems that you are calling over is half. So the size of this problem is n divided by 2, and the size of this problem is n divided by 2. Right? If the size of the original merge sort, just assume that this is n. Because you are calling the same function, I can argue that the time for calling the same function here, I can write it in terms of t, right? But what is the size of the problem? The size of the problem have been divided by 2. So I can actually say that I have 2n divided by 2 plus theta n, which is the cost of merge sort. Okay, so basically I found a recursive kind of relation for t of n. You know, everything that I discuss here about the time complexity of the merge sort is probably beyond the scope of this course. So I don't really expect you to exactly know how to do the analysis in this way. I just wanted to show it to you. Even if you didn't get the idea properly, try to actually watch the video more and more. If you still don't get it, come to the office hour. I'm going to actually explain it to you. But don't worry, even if you didn't get it completely, this is probably not something that I'm going to ask you to do in the exam of this course. In the higher level courses like COMP 359, you will see a lot of examples similar to this and learn that how to analyze the time complexity of recursive algorithms, something like the merge sort. So this is the full that recursive relationship that I have showed you. You can see that t of n is going to be 2t of n divided by 2 plus theta of n. And, after getting a recursive relationship like this, I can simply solve this one by substitution, which is going to be, these steps. So I would replace t of n divided by 2 with something similar to that. So t of n divided by 2 using the same recursive relation will be 2t of n divided by 4 plus some constant n divided by 2, right? I just replace wherever I have n, I put n divided by 2 instead of that. You see, wherever I have n, I put n divided by 2. So theta of n divided by 2 is going to be 2 theta of n divided by 4 plus c n divided by 2. I can now get this formula and put it instead of this formula here. Okay, this is exactly what I did. And if you just multiply these two inside, you will get this formula. And the reason is that these two will be multiplied and remove this one. So you get Cn and you get another Cn here. So you get a very nice formula like this, that after one step, you get this. If you repeat that after 2 steps, you get this formula. So you can see that this is very nice, that some powers here and the value here is exactly the same. At the end, after a couple of steps, you would get 2 power k, t of n divided by 2 power k, c multiplied by k by n, where you can see that this k is the same as this power. How much you are going to make your problem smaller and smaller and smaller until you reach to n equal to 1. So whenever n divided by 2 power k reaches to 1, you would stop. So in this case, what is going to be the value of k? The value of k is going to be log of n in base 2. So I basically need to replace k in all of this formula with log of n. So in total, the time complexity is going to be c multiplied by n log n. The time complexity of the merge sort is going to be n log n. It might not actually look as simple as I mentioned here, but try to do this substitution step by step. You will see that this is not really complicated. Only if you do it step by step and do all of those substitution. So this is going to be the summary of the merge sort. The time complexity of the merge sort is n log n. And interestingly, if you think about this problem, there is no worst case, best case, or average case scenario, which means that the merge sort doesn't care if the array is already sorted or if it is sorted in decreasing order or whatever is the shape of the original array or the order of the items in the original array. The merge sort always divide to 2 parts, sort first part, sort the second part, merge them. That's why there is no difference between the best case, worst case, and the average case. Always the time complexity is going to be n log n in the case of the merge sort. only the last comment that I wanted to actually leave here about the merge sort is that the idea of the merge sort is brilliant. The merge sort was the very first sorting algorithm that the computer scientists found that works in n log n time complexity, which is way better than n power 2. But still, there is some issue with the merge sort. Clearly, merge sort is not in place, okay? Because you can see that merge sort is not in place because the method merge needs additional array. Remember, the merge actually get 2 arrays and just copy those 2 arrays in a larger array. So this temporary array that you create, merge sort is not in place. The other issue with the merge sort is that the cost of the merge sort itself is really high. I'm not actually talking about the time complexity. Just comparing to some other sorting algorithms like the quicksort, merge sort, quicksort, we will see that the time complexity of quicksort is also n log n, but merge sort is going to take more time than quicksort usually in practice when you are running it over the computer. And when you are actually working over some smaller size problems, usually actually the size is 50. If the size of the array is less than 50, a method like insertion sort is going to be much faster. So even in the built-in functions, built-in functions in, for example, like C++, Java, Python, in all of those built-in sort functions, the implementation is in this way that if the size of the array is smaller than some threshold, for example 50, they would use insertion sort instead of the merge sort or quick sort. If the size of the array is bigger than that threshold, they use a merge sort or quick sort. Basically, it is, the algorithm that they use is some specific form of the merge sort with some modification. This is not exactly the merge sort that we discussed here, but some modified version of the merge sort. So next week we will talk about the quick sort, which is basically a modification over merge sort, which helps to get rid of the merge and make sure that the sorting algorithm can be done in place. At least it doesn't actually use some additional array. So I'm going to stop this video. There are some additional extra slides here. You can check them. It shows basically how to run the merge sort over some larger array like this. Just try to check these slides. It helps you to digest the idea better how the merge sort works.